So chapter 3 is where we start to really understand how wind works. We're also going to be doing some math, which will help that understanding. The chapter begins on page 23, and you're going to want to read the entire chapter at least once, maybe twice, maybe more. First thing we'll talk about is what heat transfer is all about. Well, what's heat transfer have to do with the wind? Well, wind is actually an example of solar power. And that's because wind is going to flow from warm to cold. And there's some other things we need to realize, that warm air is less dense or less heavy than cold air. And I think we've all heard the phrase that warm air rises. And so again, this is all solar power because we know the sun is what's heating the earth. And so that's what's causing all the wind. It's more exaggerated along lake shores and coastlines because of this land to water relationship. And that's because that the land is going to cool and heat a lot faster than the water. Water takes a long time to react. If you've ever listened to a weather report out of an area like Milwaukee or Chicago, you notice they'll always mention cooler near the lake in the summertime. Another place this occurs is in mountain valleys. And this is because the sun is going to heat up the sides and the floor of the valley, and that's going to cause the warm air to rise up to the top of the mountain and be replaced by the cool air. So the cool air that was above will fall down, and then at night this whole scenario is just going to reverse itself. Okay, and so that makes putting wind turbines in these areas an ideal situation in many cases. Now, what's even better is if we can have these winds, right, the prevailing winds, coincide with mountain or valley breezes, and we can come up with some very nice wind sighting locations. Here's an example here, right? This is nice, an awfully nice photograph. Older machines, you won't see new machines being put up on towers like this so much. This is another old shot. This was taken, these turbines actually still exist. This photo could have been taken near Palm Springs. There's a view just like this right off Interstate 10. I happened to drive by it here last month. It was pretty nice to see all those turbines. So a little bit more about ridges, about these hills and valleys. The wind speeds are going to increase up and over a ridge, but not until they get near the last 1/3 of the summit, right? So because of that, we want to make sure where we put the turbines because turbulence can be a real problem. We don't want to put the turbines near the foot of a ridge, and we don't want to put it on the leeward side, right? It's got to be on the windward side. Another thing that we can do is if we can have a place that coincides with both a ridge and perhaps a body of water like Lake Winnebago. The first wind turbine I was ever involved in installing took place in Chilton, Wisconsin, and which was on the eastern side of Lake Winnebago, and it was an excellent place for a turbine. And there's a link right here that explains why that ridge occurs there, and that link talks about what's known as the Niagara Escarpment. Pretty interesting ridge. And it affects not only the state of Wisconsin, but other places in the Midwest. So, what is it about wind? Wind really isn't variable. I mean, it is variable. It's not intermittent. Yes, it turns on and turns off, so to speak, but all that means is it's going to pick up in velocity and slow down. And that can vary from day to day, from day to night, different months of the year. Typically, the wind will die down the day after you put your wind turbine in, or so it will seem. Weather systems and fronts can also cause some of these problems, and in order to determine how fast the wind is blowing, we're going to have to figure out how to measure it. When we look in our textbook, see if I can find that here. Our textbook here, we're going to see that wind speed units on page 27, we're going to refer to 1 knot, 1 nautical mile, as 1.15 miles per hour. Most of the time we will refer to the wind speed in meters per second, and as we can see on page 27 here, 1 meter per second is equal to about 2.24 miles an hour. So we'll either be dealing with meters per second or miles per hour, not so much with kilometers per hour or knots. There are some conversions that are in the textbook at the start of the appendix. There's this metricconversions.org, and if you've got a smartphone, you can probably ask Siri to do it for you. Another way we can find out where the wind is we can collect data. And it used to be we would want to collect it for a year. And perhaps it still is that way. If a company was thinking about putting in a large wind farm, they would want to know what the wind is like. So we can do that with the use of met towers and anemometers. Alternately, you could put up a small wind turbine and see just how much power that you're going to generate with an inexpensive turbine compared to putting all that money into, say, a large multi-million-dollar unit. So, power from a wind turbine. This is the formula. And so these are the letters that we're going to use here. Capital P stands for power, and the Greek letter RHO, rho, is going to refer to the air density. And that is going to combine not only the temperature, but also the humidity and the altitude of where that wind is being measured. We also need to determine how much power we're going to get out of a turbine by the area of the rotor. That can be measured in square meters or square feet. And then finally, we have to look at the time period. We're going to ignore that for a little while. Notice I've got this in red, that the wind speed is in red. So as we look at this formula up here, the first line of it is before it was simplified. So 1/2 times the air density times the area of the turbine rotor times the velocity of the wind times some time times the velocity of the wind squared. Now the textbook actually shows how both of these, how this formula got put together. But so v squared, in the top line here when we have v squared, because we're multiplying that times v here again, we're going to actually be able to simplify it and just used v cubed, or multiplied that whatever wind speed multiplied by itself 3 times. So P/A is known as the power density, and notice we've taken the T piece out of this, right? So 1/2 times the air density times the area times the velocity of the wind cubed. So we know that wind has a mass, and we know that there's some energy in there, and we know that the wind can do this work. Now, I want to point out on page 30 of the book that we've got a lot of sidebars. And so here on page 30 it says wind speed notation. So every page Paul uses a lot of these sidebars here, and there's some details that are sort of hidden away in this, and so we have to make sure that we read about these and don't just think that they're extra pictures. No, there's some good factual stuff we have to dig out of there, especially this one down here at the bottom of page 30. And so here we're going to see that at sea level, with a temperature of 15 C, which is 59 degrees Fahrenheit, where the air density is as shown here, that the power density, PA, in watts per area of the wind stream is as follows. And what I want you to realize is all three of these, it's all the same speed. So for a given speed, we could measure the power in watts, the area in meters squared, and the wind speed or velocity in meters per second. Well, whether it's going 2.24 miles per hour or 1 meter per second, that's the same amount of energy. But because we changed that unit of measurement, if we want to calculate for the PA when the wind is measured in miles per hour, then we have to use this multiplier, 0.05472. And lastly, if we want to calculate if the area is in square feet and the wind is in miles per hour, we have to use the 0.00508 times the cube of the wind velocity. So that's one of the sidebars that Paul uses here that I want to point out. We're going to use this very one here again. Now on page 35 of the book, there is there's a great example of how when we average wind speeds together, that it that things can get uh, confusing. So I'm going to go back to the textbook here, and on page 35, I want to show you this formula at work. All right, so here on the next page, and I've highlighted this a little bit. Okay, we're going to calculate the power density, P slash A, and that is the rate at which energy passes through a unit of area. And we're going to do two things. And notice in this first one, we're going to take and determine what is the power density of a wind speed of 15. Now, it doesn't matter if it's 15 miles an hour or meters per second here. We're just going to say 15. So if that's the case, if I do 1/2 times whatever the density is times v cubed, right? V cubed is going to give us what that would be. So 15 times 15 times 15 is 3,375. I can do that using my calculator. There's a couple ways of doing that. I could either use, I'm going to show you the calculator that I've got here, right? So I'm going to use this calculator here. This is in the Mac machine. Sorry about that. So I'm going to clear it out. And so in this case, I'll take 15 times 15. And when I do it one more time, times 15, the answer is 3375. Well, I can also use this feature right here. This is x raised to the third, right? So I can do 15 cubed, takes me right to it. And other calculators use this feature here. This is really a handy feature. It allows me to raise a number to another number. So again, I'll clear this out. I'll say 15. I'll hit this y raised to the x power. So when I press this, that means I'm taking y, which is 15, and I'm raising it. See that character right there in between the y and the x? That's called a caret. And I then put in the number 3 to say that I'm raising it to the third power, and I get the same answer. So some of your calculators are going to have this x to the third. Some of them are going to have this y raised to the x. And some others will also just have that caret feature, which function, which we saw looked like this right here between the x and the y. All right. So back to my point. So we can see we got the 3375. Right, there's the 3375. Now, so that's the amount of energy that's in the wind when it's blowing 15 miles an hour. Well, what if the wind blows half the time at 10 miles an hour and half the time at 20 miles an hour? Doesn't that average out to be 15? Well, certainly. So, but watch what happens to the power density when we do this. When we do this, we're going to take 1/2 times the density times 10 cubed plus 15 cubed. We take that sum and we divide it by 2. And they're just putting those same numbers in here. So 10 cubed is 1,000, 20 cubed is 8,000, right? And when we add those together, we're going to have 1,000 plus 8,000 equals 9,000 divided by 2 is 4,500. Wow. So even though a 10-mile-an-hour wind and a 20-mile-an-hour wind average out to be 15 miles an hour, I'm getting more power here. I'm getting 4,500 rather than the 3375 that we had up here. So if I divide the 4,500 by the 3375, it's going to show me that I have an increase or a new density of 1.33. Well, what does that mean? That means that I have 33% more power because I had these wind gusts of 20 miles an hour. So a place that has a constant 15 miles an hour wind is not going to have as much power or energy in the wind as a place that has periods of time where it's only 10 miles an hour and other periods of time where it's 20 miles an hour. So those gusts really help us out. So let's go back to the old PowerPoint here. All right. So a little bit more about density. Cold air is more dense than warm air, so Alaska better than Arizona. Lower elevations are more dense than high elevations. New Orleans better than Denver, unless you're a field goal kicker. Humid air is more dense than dry air. Um, Memphis has uh, heavier air than Las Vegas. So cold, humid air and low elevations are ideal. And if I can be near a large body of water, that helps even more. So another thing that we need to worry about is the swept area of the rotor. Okay, and we're going to see that that's going to be calculated. We can do it in either square meters or square feet. And the formula is going to be pi times the radius squared, which is half the diameter. Um, and something you need to realize, if I double the size of the collector, the rotor, I will double the available power. So we have a conversion here of 1 meter is equal to 3.28 feet. So this formula is explained on page 33 of the textbook. So here we are. We're back to our big formula for power density. Because we're using V cubed, anytime we get a doubling in the speed of the wind from 10 miles an hour to 20 miles an hour, we are going to get an 8-fold increase in power. And again, raising that to the third power, I can either use this caret, which looks like this, or we can use y to the third. All right, so as far as wind speed, well, the wind is normally referred to as their annual average. And it's explained quite well on page 37 just how a distribution or a frequency known as the Raleigh frequency or the Raleigh wind speed distribution. So, excuse me, some of the things that are going to affect this wind speed will be turbulence and friction of items that are on the ground, and how fast it is. And we've learned that wind speed is going to increase with height. And there are ways to calculate for this. And that phenomena of the wind speed increasing with height is known as wind shear. And so we can use wind shear calculations to extrapolate and calculate for that. Anytime we're going to have a friction and turbulence decrease, wind speeds will increase. And so what's going to cause that? Well, buildings can cause that, trees can cause that, crops can cause that, bodies of water, snow, corn versus a plowed field, many examples. So on page 39 of the book, it begins discussing energy density. So it's going to show us that we're going to use an example here from the middle of page 39. And so we're going to use a density of 0.00508. Okay, that's the density of the wind that would get multiplied times V cubed, multiplied again by this EPF known as an energy pattern factor. And the energy pattern factor we'll use most of the time is that from that Raleigh distribution, which happens to be the number 1.91. So if a site has an average annual wind speed of 4 meters per second, which is about 9 miles an hour, the annual power density is going to be calculated as follows. We're going to take, all right, so notice in this example, we're measuring the wind speed in meters per second. Remember back on page 30, I told you about that formula? Let's go back and look at that. Let's go back up and look at that formula. This guy right here. Okay, so here if I want to measure the wind speed in miles per hour, I would use the 0.00508. If I wanted to measure it in meters per second, then I would use the 0.6125. So back to the PowerPoint. Aha, if the average annual wind speed is 4 meters per second, then I have to use the 0.6125 times the velocity cubed, that would be 4 cubed, 4 times 4 times 4, times the energy pattern factor, and then lastly that's going to come up to be 75 watts per square meter of rotor, right? Per square meter of rotor. Once we've got that number, we then multiply it by the number of hours in a year, 8,760, and we're going to multiply that times what a kilowatt would be, right? So 1 kilowatt divided by 1,000 watts ends up to be 0.001. This is a formula you are going to have to use for some homework this week. So when we multiply all this out, we're going to find out that there are 656 kilowatt hours per square meter of rotor. So all we have to do then is multiply this times the area of the wind turbine rotor to determine what the annual energy density is going to be, as shown here. So there's a good example of how we can do that. Notice the taller the tower, the bigger the increase in the power available. Now, I keep talking about how the wind speed changes the higher I go. And so that's referred to as wind shear. And there is a formula, there is a symbol for that that's shown right down here after the parenthesis in this formula. That's the wind shear symbol. And what's shown here is one way to calculate wind shear using the power equation law. We're going to take the velocity of the reference, meaning the known height, meaning maybe I measured the wind off of a 30-foot tall tower, and I have that number. And I'm going to multiply that times a ratio of the height of where I want the tower to be, divided by the reference height. Again, that would be that 30-foot tower. So I'm going to take that quotient and raise it to the power of the wind shear, and that's going to give us what my new velocity will be. All right. So if I know the height and the speed at one level, I can then extrapolate what it's going to be at another level. There's a good example of that in the book. So anytime I'm going to increase the wind speed from doubling the height, it's going to be calculated like this, right? So if my new height is 20 and my original height was 10, 10 divided by 20 is 2, raise that to 0.14 and multiply that times our original velocity, right? So if at 10 feet the wind is 10 miles an hour, then what's it going to be at 20 feet? Well, it turns out that we end up with a 10% increase in the wind speed. And a 10% increase will yield a 33% increase, because remember, we're going to cube that. The velocity of the wind gets cubed, so that's a 33% increase in the power available in the wind. There's another way we can calculate for wind shear, and this is using what's called logarithmic extrapolation. So if I know the heights and the wind speeds of two anemometers, I can calculate the wind shear exponent using logarithms. And there's a really good example of that on page 45 of the text. And depending upon the kind of calculator you have, will determine how you do that. Here's an example of what some of those wind shear exponents can be. This is taken right out of the textbook, so you don't need to try and write this down. It's in your books. And now as far as wind data, where do we get it from? Airports will sometimes publish it for free. Sometimes they'll ask for money for you to look at their stuff. You can get information taken from military bases, from weather stations, from air quality monitoring stations, from government energy offices, even universities and technical colleges. Like, how about here? Right? So this is our wind turbine in Fort Atkinson right here, spinning away. There's the Northwind 100. Here's our little Berge XL with an anemometer here, another anemometer here, and another anemometer here. When we look here, we are going to see that anemometer number 1, which is 30 feet from the bottom, isn't functioning. Anemometer number 2, we've got about 10-mile-an-hour winds. It's peaked at 18, and notice at 87.5 feet from the ground, it's a little bit taller. Okay, so that's another way we can find out what the wind speed is. A lot, and even some nonprofit organizations will have one. For example, this is the Midwest Renewable Energy Association, and they have a turbine set up on their property, and they have 3 anemometers placed, one at 46 feet, one at 66, and one at 86. So here about, see, this turbine's been up for quite a while. So here about 14 years ago, we could see just how the wind speed was recorded for those 3 heights. Higher we go, more wind we have. All right. Now, when you go to survey your site, and we're just going to briefly talk about this in this chapter. We have a whole nother chapter 13, that is, that will go through this in greater depth. But one of the things we can do is we can look at the vegetation. And specifically what I mean by that is the trees. As you're driving down the highway, you're going to learn to look at trees altogether differently now because you're going to learn about what flagging is and brushing. And we're going to see a picture of that here on the next slide. Another way we can do this is using the measuring instruments like we just showed at the college's wind turbine installation. Or you could literally put up a small wind turbine and measure the amount of power that comes out. And so this is an example out of Paul's book where we look at what happens to the shapes of trees. And we can see this quite often if we look off into the distance and perhaps at a fence line between 2 farm fields, or just off in the horizon you'll see trees and geez, they just look like they're always bent over a little bit or a lot, or their branches are shorter on one side than the other. Start paying attention to that, and you'll see, on your own location, maybe there are some good locations for wind where you live, and so definitely worth looking at. And one of the last things I want to talk about here is that turbulence. The wind turbines don't like turbulence. So if I had to put a wind turbine up right next to my house, I want to make sure that it's at least twice as tall as the house because that turbulence is really going to bother it. We'll talk more. There's another rule of thumb that we'll talk about a bit later. But for now, this is a nice image to demonstrate just how far away we want to have our turbine from where the